Back when we started this chapter, we talked about theoretical probability as a way of figuring out the probability of an event as opposed to empirical or experimental probability. There was a formula for finding theoretical probability. Somebody find it for me, tell me what it was. We had three kinds of probability. We had empirical, we had theoretical, and we had subjective. The formula for theoretical. What was it? Aha! The number of favorable outcomes divided by the number of possible outcomes. So, the number of outcomes in my event divided by the number of outcomes in the whole sample space. So, if the sample space is fairly small, this is easy to count. What happens when the sample space is fairly large? How do I know number of things in S, much less number of things in E? As crazy as it sounds, counting is not obvious, not intuitive. But there are some direct rules for how to count large sets. Here are 5 standard 6-sided dice. I want you to roll all 5 of them. How many different ways can that turn out? A lot, right? So let's start small. How many possible outcomes are there here? Just 6, right? Assuming this is fair, a theoretical statement, they should all have the same chance of happening, chance of any one of them out of all 6 of them. Why 36? Yes, 36 is correct. Why? So let's suppose I have 2 different experiments. And experiment 1 can happen in N1 ways, the number associated with experiment 1. Experiment 2, N2 ways. And I can keep going for as many as you want. But let's just start with 2. Then, both happen in n1 times n2 ways. So Grant, you're exactly right, because there are 6 options for the first die, and there are 6 more options for the second die, and the dice don't talk to each other in any reasonable way. There's no psychic connection between green and yellow here. They just both give me separate outcomes. So what happens when I bring on die number 3? How many possible results are there now? Six times 6 times 6, 6 to the 3rd power. 216. Grab your calculators. We're going to need them as we go on. Another 6 and another 6. And all of a sudden I'm playing Yahtzee and I've got a crap ton of options, right? If I have 5 dice, how many possible outcomes are there? 6 times 6 times 6 times 6 times 6. 6 to the 5th is 7,776 ways. But even if I'm not counting dice, we can count any large set. Who here drives regularly? Do any of you have a custom license plate? What does a Pennsylvania license plate look like? You have looked at your own license plate. 3 letters and 3 numbers? It's 3 letters and 4 numbers. Okay, wait a minute. 3 letters, then there's that funny little keystone symbol in the middle, and then 4 numbers. A question for you. How many different Pennsylvania license plates are possible? Assuming no restrictions on the license plates. How many different license plates could you have? A lot, but I need to keep track of that. So let's see if we can come up with it. Grant? Unfortunately, no, because that we haven't even gotten to factorial yet. I'm just doing regular multiplication. I'm going to treat each of these as if they were their own separate event, their own separate experiment. How many ways can we fill in this blank? And this blank? And this blank? Aha! So with all of these options, I can actually calculate exactly how many license plates are possible. 26 times 26 times 26 times 10, 10, 10, 10. What do you get? You all have your computers and phones in front of you. What is the population of the state of Pennsylvania? Because 0 is an allowable number. There are only 13 million people in the state of Pennsylvania, and there are 175 million license plates. We could give every human being in the state a license plate they could staple to their butt, and we would have lots left over, wouldn't we? Now, there is a problem to this. There's a very direct problem to this, and this is why I said there are no restrictions when we came up with this. This includes license plates that spell out rude words, or words in general. This includes license plates that look like B 88888. That goes down the road. You're going to be able to tell me what's a B, what's an 8? 00000. No, I don't want those plates, do I? So the Department of Transportation maintains a list of license plates they won't use. New license plates right now are being issued with the first letter M. And just a couple weeks ago, I was looking at license plates and I saw MN something. And I said, oh, then the next license plate that I see should go to MO. And they didn't. They skipped directly from MN to MP so that they wouldn't spell out any words. So there are a whole set of license plates that they just never issued. You logged into your computer, right? And you turn it on. How long's your password? Pretty damn long nowadays, right? It used to be a requirement that passwords were only letters. Back when we first started getting personal computers, or even computer accounts on mainframes, your password had to be a certain length. So here's a question for you. If you had a password that was 8 characters, letters only, how many options would there be? How would you get the number for this? Right? Now, my computer is stupid. It doesn't know uppercase from lowercase. So how many letters are available to me? 26, right? Each of the different spots would have 26, 26, 26, 8 times. 26 to the 8th power is a really big number. This E11 means 10 to the 11th. The exponent on a 10 is 11. So I need to move that decimal place over 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2 more. That's 208 billion passwords. If it knew uppercase from lowercase, how would this change? Careful. I don't double just the number of passwords. I double each option. Each letter could be uppercase or lowercase, right? So instead of 26 to the 8th, it's 52 to the 8th, which is, by the way, a lot larger of a number. That's 53 trillion possible passwords. This, by the way, is why brute force is a really bad way to try to break into somebody's computer account. You have to try them all. Now, you're at Seton Hill. Your password needs at least one uppercase letter, at least one lowercase letter, at least one special character, and at least one number. How many numbers are on there? 0 is a valid option, right? So there are 10. So I'd have to add one of these slots might be 10. But then how many special characters are there? Exclamation point, quote, brackets, parentheses. There are a whole bunch extra of those, right? And you don't have to just use one, you could use more. And thus the number of passwords goes up and up and up and up. Now again, some of these passwords are going to be pretty stupid, right? A is a valid option according to this setup. I don't think I should use it. 8 letters, right? Password is 8 letters. Don't do that. Grant, you said a word that I want to harp on again for a moment. You said factorial. What's a factorial? Aha. A factorial is a particularly useful shorthand for a multiplication setup. So I'm going to take the 5 dice that I have earlier, And I want you to line them up. I want you to put them in order. I don't care what order you put them in. How many ways can I line those up from left to right? How many different patterns will you see as options? I'm going to put one in each spot, yes? What goes in the first spot? How many choices? And then, aha! As I move down the line, the numbers go down by 1. The shorthand for this is 5 factorial. And we write factorial with an exclamation point. No, that's not 5. By the way, that number is 120. Now, depending on your calculator, you may or may not have a factorial button built in. On these, there is a factorial. If you don't have a graphing calculator, if you have a regular scientific calculator, your factorial might just look like X with a little exclamation point after it. But here, I type in the number I want the factorial of, and then I hit this math button on the left, third down. And there's this menu of options here. And the leftmost column is highlighted at the moment, and it says math. But the rightmost header says PRB, probability. So I'm going to move over with the arrow keys to the probability header, and lo and behold, there's an exclamation point. If I go down to option 4, it'll do factorials for me. I don't have to do the multiplication by hand. Now, this gets particularly useful when we start looking at large sets. I want you to shuffle a deck of cards. How many different possible shuffled decks of cards are there? By the way, here's an amusing fact for you. There is a memory challenge. Somebody shuffles a deck of cards in front of you, and you have, I kid you not, 10 seconds to look at the shuffled deck of cards. You can't change the order, you just get to look at them. Then you have to recite the deck from front to back. I think the winner made it through 13 decks of cards. How many possible shuffled decks of cards are there? Except it's the same property, but it uses a different number. What number does it use? Aha. And 52 factorial is a gargantuan number. You have to move that decimal place over 67 times. Those of you with your computers in front of you, I need you to Google something for me. Lifetime of the age of the universe in seconds. If you count in seconds, how old is the entire universe? Right? Just look at the length of that number. 3, 6, 9, 12, 15, 18. There are only 10 to the 18th seconds since the universe began. Since the Lord said, "Let there be light," it's only been this long. If you shuffled a deck of cards once a second, since the beginning of the universe, you would be 1 millionth of a way through the possibilities. There is a very good chance that if you shuffle a deck of cards, you are building something that no one else in the universe has ever seen. Ever. Because your sample space is effing gargantuan. What's the chance you're going to get the same shuffle deck of cards twice? So I can use my factorials to count very large sets very quickly. By the way, you can also think of these as orderings, right? I ordered the cards, the first card to the last card. I ordered the 5 dice I have. I would like to order for you, I would like to place in order in front of you all of my Olympic gold medals. Here they are. I have none of them, right? How many ways can I order no things? An empty ordering. There's one way to order no things. So from a math perspective, we often define 0 factorial to be 1, an empty ordering. That's going to come in useful in another 40 minutes or so when we get to using these counting ideas to do bigger things. Questions? Most of the card games I play, I don't get an entire deck to myself, right? You take a deck, you shuffle it, you get some cards, right? This actually is a poker-sized deck. Anybody play poker? How many cards you get? Depends on what game you're playing, right? But you end up with 5 if you're in your hand. If I want 5 cards out of a shuffled deck, then I really only care about the order of those first 5 cards. I don't care about these, right? So if I think about my ordering idea here, I could say that what I really want is to discount all of the cards after the first 5. I want to think about taking K items out of a set of N items and keeping them in order. We're going to call this ordered selection a permutation. And normally we'll write something like NPK or PNK. And I like to think of it as picking, thus P, permutation, picking one at a time, K items out of a pile of N items. So let me think about this. If I was doing 5 cards out of my deck, then I would be asking you to select 5 from 52. How many first choices do you get? How many second choices do you get? It's going down just like a factorial, isn't it? But all the rest of these numbers Those shouldn't count, right? So I need to somehow discount all of these. If I divided, those would cancel, wouldn't they? Oh, so that makes the top of this 52 factorial. And it makes the bottom 52 minus 5 factorial. There's a way to do permutations using factorials. I could also do it just by writing the slots, right? I want 5 numbers. One, two, three, four, five, right? I just have to know to stop after the 5th one. But here, this I can tell my calculator to do the calculation for me, can't I? Factorials are easier that way. There is one important thing to notice in my deck of cards. In this selection that I am making, is that no repetition is allowed. You can't get the same card twice in a row. You can't have any 2 of these be the same. That's why this changes every time as we go down our list. But if I give you 5 cards, they're yours. They're in your hand. Here are my 5 cards. Do I have to keep them in the order you gave them to me? This is an ordered selection. This keeps stuff in order. I said that right here at the top, a finite ordering. So this is an ordered arrangement. What if I don't care about keeping them in order? Here are my 5 cards again. If I can rearrange them however I want, that changes the number of things, right? Because then you could say, oh, well, I have these 2 cards, but I don't care whether I got them in this order or in this order. Those are equivalent, aren't they? I need to reduce my number of choices again. And we reduced our number of choices here by dividing. So I need to divide again. If I don't care about ordered selection and I just want an unordered selection, unordered selection, I'll take this number and divide it by the number of ways I can rearrange the things I was given. How many cards was I given? How many ways can I order 5 cards? I'm putting them in any order I want, but I'm using all of them, right? 120. My 5 factorial, right? If I was given k things and I didn't care about their order, I would divide by the k factorial ways to get that. And by the way, that means I can actually take a formula from up here. NPK is n factorial over n minus k factorial. This thing is going to be n factorial over n minus k factorial times k factorial on the bottom. We're going to give that another name. We're going to call this a combination. NCK. So I have permutations and I have combinations. Again, I'm still not allowed to repeat things. All of this assumes that your cards or items are only used at most once. Again, okay, so we did this 52.5, right? And that was here. So this is our N, and this is our K. So that gets me this formula. But now I'm saying, oh, let's take that thing and divide again. Well, dividing means multiplying by 1 over. So I put this thing on the bottom. So that's where it went from here to here. But I agree with you. The formulas are kind of messy, aren't they? Please notice combination numbers are always smaller because you don't care about the order in which you get things. Those two can be switched around. I don't want you to remember these formulas. Go back to your factorial. Go back on your calculator to where you found the exclamation point. On my calculator, I hit the math button. I go over to that PRB section, probability. Hey, wait a minute. You see what I see? They used R instead of K. Big deal. Let's talk about our deck of cards for a moment. There were 52 cards, and we got 5 of them, right? 52, math, probability. I will hit the right button, math. Permutation. If I care about the order, there are this many ways to get 5 cards. But if I'm playing poker, I don't care about the order. So instead of NPR, I'll do math, probability, NCR, 5. And this is a number that people who play poker tend to end up memorizing. 2,598,960. 2.6 million different possible hands of poker. You get all 5 cards. Now, depending on which variation of the game you play, this may not be the number that matters to you, but it might. What is the best possible hand? A royal flush. A royal flush consists of the following 5 cards: the 10, Jack, Queen, King, and Ace, all in the same suit. So, a question: how many royal flushes are possible? There's one. Just 4, right? They're either all hearts, or all spades, or all clubs, or all diamonds. So what's the chance of getting a royal flush? Well, you now know there are only 4 favorable events, and there are exactly this many total events. 4 divided by 2598960. That's a very small number. 0.000015. It's a really unlikely thing to happen, isn't it? But now you can actually know that calculation because you know the size of your sample space and the size of your event. You have a theoretical probability in front of you. In all of my years playing poker, I have gotten a royal flush once. By the way, anybody ever play the lottery in this room? Lottery tickets are combinations. You're on the internet. You need to go to the Powerball website. how many different Powerball tickets are possible? How do you play the Powerball? How do you fill out a card? You pick
6 numbers.
6 numbers. But there's something special about the way you pick them. They come in like 2 separate colors, right? There's the white numbers and the red numbers. And you only pick one red number. So it's you pick 5 from what to what? The white numbers, they go from 1 to 69. And then you pick 1 red number, but the red numbers only go up to 26. So if I asked you, how many possible Powerball tickets are there? You need to tell me how many different ways you could make these choices. Let's do the second one first. How many ways can you pick one red ball from 1 to 26? $26. That was easy, right? There are only 26 choices. But if I think of it as a combination, out of these 26, I choose one ball. I don't care what order it comes out in. That's why unordered selection here. Now let's go up to the top. You pick 5 white balls. You can't repeat one. So once the ball comes out of the hopper, you can't get it again. How many possible ways are there to do that part of the picking? I don't need a number, I just need a formula. But not P, because once the numbers come out, the order in which I got them doesn't matter. I want both of these things to happen. If I want them both to happen, I need to multiply these possible outcomes. So the total possible Powerball tickets, 69C5 times 26C1. Now I know this number. I know this because Nico told me it's 26. I just need to know what this number is. Combination as opposed to permutation. So on your calculator, do 69C5. Tell me what number you get. 11282385 13. Why do we have the feeling I have an extra digit in there?
Yeah, 1123885.
Okay, 112385. I wrote in some extra numbers. Multiply by 26 and you get a big number. 292,201,338. Yes, sir.
What's the formula for combination?
You can use either one. You're welcome. Okay, wait a second. Powerball ticket costs $2, right? 292 million possible choices. The minute the Powerball crosses $600 million, if you buy every possible ticket, and you're the only winner, you make a profit. But you have to be the only winner. I really want to go to a bank and say I have a guaranteed money-making scheme. They'll laugh me out of the building. By the way, you buy one ticket. Your chance in winning is 1 in 292 million. I went to the National Weather Service and I asked them to give me the chance of getting struck by lightning. Do you know what the chance of getting struck by lightning is? The chance of getting struck by lightning sometime in your life is 1 in 15,300. Anywhere in the country, somebody. The chance of getting struck by lightning is 1 in 15,300. The chance of getting struck by lightning. What's the chance of getting struck by lightning twice? You take that number and multiply by itself, right? I worked this out. I would like you to notice that the bottom number in this fraction is smaller than if you take this as the bottom number. Which means if you buy one Powerball ticket, your chance of winning the Powerball is less than your chance of getting struck by lightning twice. Lottery is a tax on people who are bad at math. You are more likely to be struck by lightning twice in your lifetime than you are to win the Powerball. That's nuts. Why? Why am I doing all of these counting ideas? I'm doing all of these so that I can figure out the size of a sample space, so that I can figure out probabilities, so that I can tell if something could have happened by random chance or if there was some factor involved that made this particular thing happen. How likely is it for this to have happened randomly versus for this to have happened with some cause? I don't know what that cause is, but if something happens more often than it should, then something's going on. But I need to know how often it should happen. That's what these tell me. To that end, I can talk about a probability distribution. Okay. In order to do this, I have to have a name for the thing that's happening. I roll one die. I got a number. I roll it again, right? This is a random event. Every time I roll a die, I have no control over what number is going to come up. A random variable represents the outcome from this sort of a process. You'll often hear this referred to as a stochastic process. I promise we'll define that word more precisely a little later. The book actually uses the idea that this is a function whose output is what happened in my random variable, in my process. My dice only has a finite number of outcomes. But if I were to ask you about stopping a random person on the street and asking you how tall they are, what units are you going to use to measure how tall people are? Inches, centimeters, feet, millimeters, micrometers. You could measure a person's height to a millionth of a centimeter, couldn't you? It would be a pain in the ass, but you could do it. If I have a finite number of options, that's called a discrete random variable. Things like the number of absences to a class, the number of points you scored on an exam, the number of phone calls you received in the last 72 hours, a finite number. We may or may not have a clear upper limit. I mean, if I'm talking about my 5-card poker hands, well, then there are 2.6 million options. If I'm talking about lottery tickets, there are 292 million options. But those are still a finite number of distinct options that could happen. When I roll my die, I can tell you what happens with each outcome, right? What's the chance that came up a 3? Chance it's a 3. 1 in 6, right? I want to take every one of these values and assign a probability to it. And I'm going to call that a probability distribution function. Our discrete random variable, we've named it X, now has a list of probabilities associated to each possible result. It could be that all of those probabilities are the same. I roll this die, chance of getting a 1 is the same as chance of getting a 2, etc. But if I roll 2 dice and tell you to add the numbers, then those outcomes are not all going to have the same probability. Let's let xi be one of the possible values. Then I get a probability for xi. What do I know about that number? Guarantee you know 2 things about that number. You know that that number must be between 0 and 1. Chance of it never happening, the chance of it always happening. And if you looked at all of the possible values and you added them up, what would you get? 1. Those are the same rules we had before. But now I want to look at the kinds of functions I can get, the kinds of rules I can use in probability, and I want to turn all these randomized ideas that we were talking about in chapter 5 into usable, testable results, so I can determine if something is happening more often or less often than it should. That is where we'll pick up on Friday. Please notice we have finished chapter 5 today. That means your homework is due 2 class periods from that normally would mean Monday. However, break Monday. I will see you Wednesday. Your homework will be due then. Double check your calendars. I will see you all then. I'll see you all Friday.